老师好，有看到画面吗？等一下，有吗？有吗？
有，
好
没问题。
Next speaker is Jackson presenting the paper about position information in CNN. Okay, good evening. Hello everyone. My name is Yang Jiachen. So the topic of my presentation is position, padding, and prediction. A deeper look at position information in CNNs. And this paper is published on International Journal of Computer Vision 2024. So let's get started. So here is today's outline. First, I will introduce the motivation. Then I'll go through a series of hypotheses, experiment, and result, followed by conclusion and comment. So the topic is like this. 好慢。Notice that it used the word deeper. So why does it use this word? And what is it being compared to? Remember last time I presented another paper called How much position information do convolutional neural networks encode? Let me briefly recap for everyone. So the author proposed a hypothesis that they try to train a network so that given any image input, the model can output the ground truth position maps, which contains the axis information. And the ground truth position map contain the distance information in a certain direction. For example, the edge position map contains absolute information along y-axis. And they use fixed pre-trained weight. And train a simple convolution, for example, 3x3 kernel, to test if the FPOS component can extract absolute position information from the multi-scale feature map. And result shows that PostINET can extract positional information consistent with ground truth position map only when coupled with a deeper encoder network. And the author proposed a hypothesis that the padding near the border delivers position information to learn. And it seems that the hypothesis that zero padding delivers position information makes sense, because you can see that if we have padding here, we can extract more position information than the network without padding. Hence, there are some conclusions from last presentation. First, they verify the hypothesis that absolute position information is implicitly encoded in a convolutional neural networks. And second, the readout of absolute position, which is very strong from a trivial single layer 3x3 postnet. And last but not least, the result indicates that zero padding provides position information, and this effect is more obvious in saliency detection and semantic segmentation tasks. And if you really forgot the content I presented last time, here is the recorded video for you. And don't forget to like, comment, and subscribe. So now let's get to the point. So this paper mainly extends the previous one with a deeper discussion and analysis. They propose several hypotheses, and let's dive into each hypothesis one by one. First of all, does zero padding encode maximal absolute position information compared to other padding methods? The method is that they first pre-train a model on VGG5 classification task using different padding methods like zero, circular, reflection, and replicate to get the pre-trained weight for FENC here. And second, they fix the pre-trained model's weight here and train the position encoding module to extract positional information. Therefore, this experiment aims to compare which padding method can extract the most positional information. So in this figure, it is clear that zero padding delivers the strongest position information. And note that partial convolution is still kind of zero padding, but it scales the value after convolution. And I will explain what partial convolution-based padding is. So partial convolution-based padding, in short, is first pads with zero, and then do the normal convolution operation. And after that, the scaling factor is compute. They scale the value after convolution using a scaling factor. And the scaling factor is computed as this. For example, what is the scaling factor of this pixel? It simply is you use kernel size and divide it by the number of non-padding pixels. For example, if we use 3x3 kernel, the kernel size is 9, and the number of non-padding pixels is 4. So the scaling factor is 9 divided by 4. So after you convolution with zero padding, you should multiply the value with a scaling factor. So this is the idea of partial convolution-based padding. So we have now validated that the hypothesis is that zero padding encodes maximal absolute positional information. And another finding from the figure is that circular padding is often the second most effective padding type for providing position information. They think that this is because it uses the value from the opposite sides of the image, where the pixel values are usually less related to the nearby pixels. As a result, circular padding often causes a noticeable change at image border, unlike reflection and replicate padding. They use a similar pixel in the border. So since the boundary effects and position information in CNNs are still not fully understood, they study the location-dependent test for position analysis to test the hypothesis 2 to 4. And here shows the big picture of the experiment setting. They designed an experiment where images are placed into different grids. In this case, it's a 3x3 grid. And then they do the classification and segmentation task. But there are no, in this case, there are no segmentation labels in the dataset they use, which is CIFAR 10. So it was noted that the segmentation task simply assigned the grid location of each picture to its ground truth label. But what is this experiment setting for? So the goal of this experiment is to force the model to learn semantic features invariant to the grid location. So if a model can perform well on this task, it implies that this setting provides positional information to help model learn the position invariant property. And there are some different settings. They investigate the setting of different canvas and the case with or without padding. And here are some details of the experiment. They use CIFAR 10 dataset and use the VGG11 model. And during training, they randomly place data in different grid locations. And during testing, they run the entire validation sets of CIFAR 10 on each individual grid location. And the task, as I mentioned before, it includes classification and segmentation. So the result will be shown in a chart like this. And let me explain the meaning of each item in this table one by one. So the number here represent the different grid size. For example, 3 by 3 grid size, 5 by 5 grid size, like this. And there are different grid size settings. And the character here represent black, white, and min, respectively, which refers to the different canvas setting. For example, a black canvas background, white background, and min background. And the padding must be applied during the VGG11 training process to maintain the size of feature map. So the without padding here refers to using bilinear interpolation based no padding. And this padding involve first aligning this picture to the border and following by the bilinear interpolation. So now we have fully understand the meaning of this chart. So let's look at the result. So as I mentioned earlier, if a model can perform well on such a task, it implies that this setting provides positional information to help the model learn the position invariant property. So you can see that for all canvas, the network trained with padding are more robust to change in grid size. And it implies that zero padding can provide strong positional information, allowing the performance to maintain even when the grid is larger. And the model trained without padding under white and min canvas setting significantly drops in performance with the increase of grid size, as the position information is lost and boundary information cannot be exploited. However, if we use black canvas, the classification performance results do not vary even in the large grid size. So because using black canvas without padding, it is fundamentally the same as having just a picture and zero padding. So it has the same effect of using zero padding. So it can maintain its performance even if the grid size is large. So now we know that if using a zero padding or a black canvas can provide positional information. And are there any other ways to provide positional information? In the previous paper, they found that the larger kernel size are likely to capture more positional information than smaller ones. So this is the result of last paper. You can see that if we use 7 by 7 kernel, we can extract more positional information. So they propose a hypothesis that maybe the receptive field can affect the ability to encode positional information. But how to design an experiment to compare the effects of different receptive field size? So we know that in ResNet, the receptive field becomes larger as the model goes deeper. For example, in this case, 2 convolution layers is equivalent to 1 5 by 5 convolution layer. So this pixel is from a 5 by 5 region here. So we can simply use a 5 by 5 convolution filter to replace 2 3 by 3 convolution filter. And there is another model architecture called BACnet, which can feature a fixed receptive field. So the idea of BACnet is simple. It classifies each independent region using a ResNet-like architecture. So every patch will be computed using the same ResNet-like architecture, and they will the patch and patch will not overlap. So they use this architecture to going through all the image, and it will eventually produce one heat map per cast. And after going through all the independent image region, it will produce one heat map per cast. So they can, if it is a classification task, it can accumulate activation over the space to yield the total cast evidence. So here are some properties of BACnet. BACnet is interpretable. For example, it is very easy to identify the most informative image patch for BACnet. For example, we can see the most important position using a heat map. For example, in a mountain bike, we can easily know which part is the most important for this cast. And another is that BACnets are another property is that BACnets are a modified version of ResNet 50 that restrict the effective receptive field of the CNN to be a fixed maximum, either 9, 17, or 33 pixels. So back to our hypothesis. The hypothesis, they propose a hypothesis that maybe the receptive field can affect the ability to encode position information. So here is a comparison. We can find that the receptive field of BACnet 33 and 17 can cover a large portion of the patch. This is why the BACnet 9 suffer more in performance, because it has no such large receptive field. And we can find that the network with larger receptive field, such as ResNet 50, and those using zero padding, can leverage absolute positional information to perform more accurate segmentation. So this hypothesis must be true, because in a BACnet's performance is not as well as the ResNet 50. And the difference between BACnet and ResNet is only the receptive field. And let's move on to the next hypothesis, whether the position information is correlated to semantic information. So the goal here is to validate whether positional information and semantic information are correlated when encoding in a latent space. The method is to estimate the dimensionality of semantic factor zk that represents this concept in latent representation. But how can we understand the semantic meaning in the latent space, which is often meaningless to humans? So by using the method proposed in this paper, we can transform the latent representation into a interpretable representation. For example, in this case, after performing the transformation, changing the interpretable Z1 digit representation of this column will allow us to generate a new image of different digits. So the information in the latent space can indeed divide the semantic information understood by human. But how can we verify this hypothesis? To be specific, in this case, how can we determine the importance of the position information and the semantic information in latent space? So if the information is very important, it will require a larger portion of the dimension in the latent space. So given an image pair like this, this pair of images share the same concept of location, and this pair of image share the same concept of semantics because they are all both. So given an image pair, we can compute the similarity in a case semantic concept. So a positive mutual information between IA and IB implies a similarity of IA and IB in the case semantic concept, which will preserve in the latent representation EIA and EIB. E is the encoder. So we can approximate the mutual information between these two latent representations, and then we can compute the dimension of this semantic factor k. And zk represents the percentage of a certain concept. In the previous example, it's like location or the semantic in the latent space. So they use these testing pairs and feed them into a differently trained model. And we can find that the model trained with zero padding contains more dimensions which encodes the semantic factor locations compared to the no padding case. Further, there is a positive correlation between the encoding of location and the encoding of semantics. That is, a larger number of dimension encoding location implies a larger number of neurons encoding semantics support the hypothesis 3. So the position information is correlated with semantic information. And the next topic is whether the boundary effect occurs at all image locations. So we want to know which location will be affected by border effects. And the test they use is a grid-based test I mentioned earlier. So to obtain the accuracy at each distance, they average the accuracy over grid location with same distance to the nearest border. For example, in this case, this picture's distance is 4. And they can use this method to test where the boundary effects suffers more. And this figure shows the difference between zero padding and no padding across 3 canvas settings at various distance from the border. And you can find that the border region suffer most from border effects. The accuracy difference is higher at grid location close to the border. Here, they are 0 to the border, and decrease toward to the image center. And zero padding significantly impacts the border effects, and it injects position information to a network as a function of the object location relative to distance of the nearest border. In contrast, the no padding case fails to deliver any position information at the border location, which leads to a significant performance drop. And also, there is a substantial difference in performance at the centers of image. Look at this column. At the farthest distance from the border. So it is obvious that the boundary effects occurs at all image location, even if the image is at the center of the grid. It will it will have a performance drop compared to zero padding. And further, the convolution cannot fully overlap the border regions without padding, and thus will not recognize object as well. We can see the feature map here. The activation for grid location 7 are significantly reduced in no padding case. You can see that this is the zero padding case and the no padding case. So the activation is blurred and is unobvious. And another case is a center case. For the location at grid location at 25, there is also a visible difference in activation space. Here, the activation found for no padding case are blurred and noisy, which contrasts to the tight square shape activation when zero padding is used. So, in short, we can validate that the boundary effect indeed occurs at all regions of the image. And finally, the last topic is whether position encodings act as a feature or a bug. Remember that Professor Chen also asked last time if simply using zero padding can accidentally contain absolute positional information. Isn't that quite concerning? So, to verify the impact of positional information on performance, they conduct two experiments to check whether the performance improves. The first test is semantic segmentation test, and the second is texture recognition. So, the experiment is to measure the impact of zero padding on segmenting objects near the image boundary and compute the MIOU for rectangular ring-like regions. For example, 0 to 5% is the region of this square ring, and 5 to 10% is the second square ring. So, in semantic segmentation task, encoding, you can find that the absolute position information enables CNNs to learn more robust semantic features. The performance drop between the total MIOU and the border region. You can see that the total region is higher than the border region, 0 to 5%. For the no padding case and the reflect padding case compared to the zero padding case. Zero padding also dropped, but it dropped slightly than reflect pad and no without padding case. And this further demonstrates that the absolute position information due to the zero padding improves the performance at all image regions, while reflect padding is not as beneficial at the image boundaries. So, in semantic segmentation task, encoding positional information improves the performance. And here is another case, texture recognition. They propose a hypothesis that since there is no spatial bias orientation in most texture recognition dataset, position information may not benefit the performance of CNN. So, they designed an experiment to evaluate the texture recognition performance of 3 models, and using different padding scheme, setting on GTOS mobile and DTT datasets. So we can find that model trained with reflect padding outperforms the model trained with zero padding. This result implies that position information may not guide the network to learn robust representation for the task of texture recognition. So in short, does encoding position always improve the performance? We can say that it really depends on your task. Finally, the conclusion and comment. Here are the key findings of this paper. First, absolute position information is implicitly encoded in convolutional neural networks. And second, zero padding encodes more position information relative to common padding types. Third, zero padding encodes more dimensions to encode position information, and that this correlated with the number of dimensions that encode semantics. Fourth, black canvas provide rich position information compared to other colors. Fifth, boundary effects have an impact on all regions of input. And last, the position information can be used to improve performance, but can be also detrimental to CNN performance if not taken into consideration. Here are some of my comments on this paper. First, this paper presents numerous hypotheses to design experiments and conduct analysis, which is worth learning from. And second, BACnet is an interesting model architecture and may be promising for interpretability in EEG signals. And there are indeed relevant papers using the BACnet to analyze EEG signals. And that's all of my presentation. Thank you.
I'm curious about the hypothesis 3 experiment. Say you use the latent pairs.
这个
Yeah, can you explain again?
就是这边就是要去算说，它有一个假设是说，如果你完成这个，就是你要进行这个任务，然后你可能会就是随着模型的加深，你会有一些资讯在 latent space。那如果这个资讯是越重要的，那你在 latent space decode 出来，应该要占的维度要越多。那他们的测试方法就是把两个语义一样的东西丢到他们已经 train 好的 model， 然后去判断说这两个东西在 latent space 的 similarity 是多少。如果去算说那个 similarity 的值，那因为他们比如说这两张图，它的 location 在一样的地方，所以如果这个 latent space 里面有关 location 的资讯，那他们算出来的那个值应该就是 location 的 dimension 的体，就代表说 location 这个资讯在 latent space 里面占了多少分量。那另外一个例子就是这都是船，所以这两个 pair 丢进去算 similarity， 应该是会算说这个语义的 concept 在这个 latent space 的 dimension 的体占了多少。那越大就代表说这里面含有这个语义的 concept 的资讯越多，这样。
后面它是就是那个表格怎么得到的结论？
哪一个？这个吗？
这个表。
哪一个结论？就是他的意思是说，如果这个 location 的 z location 越大，那 z case 也会越大，就这样而已。就是有相关，对吧？就是看这个表，就是刚好是它如果越大的话，那另外一个值也会越大，这样。就是如果 location 的它算出来维度越position 就是 location 啊 z location， 如果它算出来维度的值越大的话，那它的语义的资讯在中间的 latent space 也会就越大，就看那个数字而已。
哦，这个是在 latent 的那些
对对对对对对对对对。
Z is the dimensionality.
啊
So Z means the dimensionality.
Yeah, yes.
So I'm curious how
estimate
in the latent space.
就是他们会把假设他们会产生这种很多 image pair。那 image pair， 比如说这个 image pair 就是他们 location 是一样的，那这个 image pair 就是他们都是船，所以理论来说应该是他们的语义的概念是一样的。然后他们就把这个 image pair 分别丢入模型，然后在 latent space 里面去算它的 correlation。那算完 correlation， 如果无法知道说，不知道的 concept 就当做 residual factor， 就是剩下的是 residual factor。在这个 case 里面，他们只有分析 location 跟语义的概念，那其他概念就当做 residual。
And n is就那边有个大 N，
大
大 N 是
大 N 是什么？好问题。大 N 是什么？大 N 是什么？可能要看一下 paper。